Welcome to today's class. We will be doing a little bit of a discourse on projectile motion. And projectile motion is simply motion in two dimensions. The reason why it's in two dimensions is because as the object is going vertically, the object is also going horizontally at the same time. So as it's going like this, it's rising and going towards the left at the same time, essentially. So it's rising up and going towards the left at the same time, to be more specific and to be more precise. So it's motion in two dimensions. It's a system that combines two forms of motion together. And usually the angle of projection of the velocity is at an angle between 0 and 90. At 90, it is vertical motion. At 0, it is horizontal motion. So in between 0 and 90, the moment we just have 1 degree, 2 degree, 10 degrees, 30, 40 degrees in projection, then we are beginning to have a projectile motion. So I'm just going to give the general sketch of a projectile motion and then describe the governing equation and just introduce it briefly. Remember, subsequent video will take care of an example on projectile motion. Just hop on together with me. Let's learn the projectile motion together. And first and foremost, the general construct that governs the projectile motion is this. It's imperative that you know where it's being applied. It's actually being applied to determine the range of a bullet. It's actually being applied to determine the range of a rocket, how far a rocket can go, and if a rocket can actually meet a particular target. We use that for trajectories in particular, so to speak. So a projectile is usually projected at a certain angle with a certain speed. At a certain angle and with a certain speed. Okay, this is the horizontal component, and this happens to be the vertical component, essentially. With the removal of the assumption that governs motion, which is neglecting air resistance, two things are certain. The projectile only accelerates and decelerates along the vertical. It does not accelerate or decelerate along the horizontal. So the projectile, remember, has two parts, horizontal component and a vertical component. Let me distinguish the two parts on the table. Horizontal, vertical. Okay? The horizontal, that's we're talking about movements along the x-axis. The vertical, we're talking about movements along the y-axis. In the horizontal, there is no acceleration. There is no acceleration, so the acceleration along the x-axis is 0. In the vertical, there is acceleration, and the acceleration is plus or minus g. Being a vertical motion, the plus is for when the object is falling down. The minus is for when the object is rising up. Of course, as you can see, it goes up till it gets to a maximum point and begins to fall down. We'll come back to this diagram. Let's just describe some things briefly. Now, the horizontal velocity is simply the velocity of projection multiplied by the cosine of the angle of projection, that's u cos theta. While for the vertical, okay, and final velocity Vx has its own expression. It has its own expression. Initial velocity, the final velocity Vy also has its own expression that will derive in the next column and bring back to this place. And time is the same for both. Time is not really a component. Time is the same for whether you're moving vertical or horizontal. Time is simultaneous to the two of them. And distance along here is still s. distance along the x portion is still s, distance along the y is still h. Please, this is for secondary school convention purposes. For the university convention purposes, the x and the y are actually used in place of s and h. Now let's derive some basic formulas and then come back to some very basic definitions. Well, instead of deriving the formulas, let me simply write the formulas for ease. Vx is equal to u cos theta is the same as this. This is because acceleration along here is 0. So since the acceleration is 0, the two components in particular are the same. Here the acceleration is plus or minus g, so Vy is simply u sine theta plus or minus gt. Okay, those are the two governing equations. Now let's get back to the graph. The point where it reaches the highest point is called the maximum height. We denote that with a capital H. And then the distance it covers when it lands back at the same level from which it was projected is called the range. We denote that with a capital R. We denote the range with a capital R. That's the distance between the point of projection to the point where it comes down to the same level as it was projected. That's what we call the horizontal range, essentially, as you can see noted on the diagram. Let's do some important definition and write some important equations. The first thing we need is called time taken. To reach maximum height. The time it takes to actually get to the maximum height, TH. The time it takes to actually get to the maximum height, TH, is expressed as okay, this is the time it actually takes to move from the point of projection to the maximum height. The time it takes to move from the point of projection to the maximum height. We also have time of flight. We use a capital T. This is the time it takes to move from the point of projection back to the same level from which it was projected. So move from the point of projection upwards and then back to the same level to which it was projected. And usually this is 2 times the time taken to reach the maximum height. And so the time of flight is actually 2u sine theta divided by g. Number 3. The next important information we need is the maximum height. Maximum height is simply the highest point the projectile attained. Maximum height is simply the highest point attained by the projectile. The highest point attained by the projectile. So we have that h is equal to u square sine square theta over 2g. This can actually be proved. All these formulas can be derived from this relationship. Essentially, commit the formulas and the definitions are stated to memory. Then we have the horizontal range. This is the horizontal distance between the point of projection and the point of landing. The horizontal distance between the point of projection and the point of landing on the same level. The horizontal distance between the point of projection and the point of landing on the same level as it was initially projected, and the horizontal range is denoted by R, and that is represented by U square sine 2 theta over G. U square sine 2 theta over G. These are the paramount equations that are actually being needed and will be requested from you. Some questions can go further to request some more intricate portions and some more intricate calculations. We're going to see how those ones surface. That means they can actually request for things that will involve you doing some calculations of this particular format, so to speak. Thank you for watching the video. Please like and share. You can actually contact us on the page that actually will be after this video, the phone number on the screen and the address of the Facebook page. Thank you for watching.